Hello friend, welcome to this lecture, and in this lecture also we will discuss the Lyapunov stability for dynamical system. And if you recall, in previous lecture we have discussed some say definition related to Lyapunov function v of x. We know that what is positive definite, negative definite, positive semi definite, negative semi definite, and how to find out v star, which is the derivative of v along the dynamical system x dash equal to f of x. And we have considered one theorem which simply says that if we are able to find out a Lyapunov function v of x which is positive definite in a say spherical domain, say SR, sphere of radius r, such that Vx is positive definite on S of r, on and inside S of r, and V star is less than or equal to 0, then the 0 solution of x dash equal to f of x is stable here. In fact, if you look at geometrical way to look at this thing, so here we simply say that since it is depending on V of x here. So, V of x is negative definite, means it is taking only say greater than 0 for x non equal to 0, and it is 0 when it is x equal to 0, and V star x is less than or equal to 0. Now, V star x is basically what? It is basically del V dot f of x here. Now, if look at Vx greater than 0, so it basically let us take n equal to 2 now. So, V of x is basically represent a kind of a surface, and that surface include your 0, because when x is equal to 0 then it will reduce to 0 because V of 0 is equal to 0. So, let us consider say V of x equal to some c here, where c is certainly positive. Why? Because Vx is positive definite. So, it will take only the non-negative value and it will take 0 value only at the origin. So, it means that here Vx equal to c, where c is positive. So, this will represent a surface which will contain origin here, and if you look at this V star x less than or equal to 0, then this del V represent basically the normal vector pointing outside to this thing. So, at this point this del V is this. So, del V is this. So, del V is del V. Now, del V dot f of x is less than or equal to 0 means what? That the angle between the normal vector and f of x is more than 90 degree and less than 270 degree. So, it means that the f of x, which is a vector here, it must be say no way it is say outside. In fact, it is heading towards the inner of V of y, V of x equal to c. So, it means that this f of y, f of x vector is say directing inside the domain Vx equal to c here. Now, what is this f of x? If you look at f of x, it is nothing but x dash equal to f of x. So, it means that f of x is nothing but the tangent vector of the x dash here. So, it means that at this point this x dash represent, this f of x represent the tangent vector defined at this particular point. So, it means that the tangent vector is directing towards your interior of Vx equal to c. So, it means that at no point on the boundary here your tangent vector is directing outside or outside or trying to take say outer region. So, it means that at every point on the boundary your tangent vector is always directing inside your Vx equal to c. So, it means that solution, if it start inside Vx equal to c, then tangent vector always to say direct towards the interior of Vx equal to c. So, it means that it is always try to remain in Vx equal to c only. So, it means that it is never going to be unbounded. So, that is what we can say that the geometrical way of looking the theorem number 1 here. So, now let us consider some more theorem based on Lyapunov function. So, first theorem we have already discussed, which says that if there exists a scalar function v of x which is positive definite on a sphere of radius r and v star x is less than or equal to 0, then the 0 solution of x dash equal to f of x is a stable solution. That is what we have proved in theorem number 3. Now, let us consider one more theorem, and this time we are not giving any proof of this. For proof we can say refer some very good book, that is one book given by Prover and Noel. It will, you can obtain the reference of this book in our the reference list. So, this theorem number 4 says that if there exists a scalar function v of x which is positive definite and v star x is negative definite on S rho, where S rho is defined as a sphere of a radius less than epsilon, then the 0 solution of 1 is asymptotically stable here. So, this simply says that if Vx is there, which is positive definite, Vx is positive definite and V star x is negative definite, then the 0 solution is asymptotically stable. So, here it is asymptotically stable, and earlier we have proved that Vx is positive definite and V star x is less than or equal to 0, means negative semi definite, then it is a stable solution here. And then we have one more. So, here we are just stating this theorem number 4, we are not proving the theorem number 4, and in the same way we can define theorem number 5, which is given the instability of autonomous system here. So, if there exists a scalar function v of x such that v of 0 equal to 0, here we are not requiring any say positive definiteness or negative definiteness of this scalar function, such that v star x is either positive definite or negative definite on S rho, and if in every neighborhood n of the origin where n is contained in S of rho, there is a point x naught such that V x naught has the same sign as V star x. So, if I assume that V star x is PD, means positive definite, then we can find if there exists a point in the neighborhood of origin such that V x naught is positive, then 0 solution is unstable, and if we take V star x as negative definite and there exists a point x naught such that V x naught is less than 0, then also the 0 solution of 1 is unstable. Please look at here, the requirement that Vx is positive definite is removed here. Here we just assume that Vx is a scalar function such that it is vanishing at 0, that is all. So, everything here is given in terms of V star x. So, V star x is positive definite and in a neighborhood of origin there exists a point such that Vx naught is positive, then your 0 solution is unstable, and if V star is x is negative definite and V x naught is less than 0, where x naught is a point in the neighborhood of the origin, then the 0 solution is unstable solution here. So, again I am not giving the proof of this, we are just discussing some example based on the given theorems here. So, here consider the 2 dimension system here, x1 dash equal to minus x2 plus x1 r square minus x1 square minus x2 square, x2 dash equal to x1 plus x2 r square minus x1 square minus x2 square. Now, here r is some constant, r is some real constant here. So, now here let us choose the positive definite function v x1 x2 equal to 1 by 2 x1 square plus x2 square. So, here most of the cases we define your Lyapunov function, the function v x1 x2 as say quadratic form, and we have discussed the quadratic form is summation say bij xi xj and I comma j equal to 1 to n, and this is a symmetric form. So, here let us in this case when n equal to 2, we simply define v x1 x2 is 1 by 2 x1 square plus x2 square on r square. Then we can calculate v star x1 x2 as minus x1 square plus x2 square, x1 square plus x2 square minus r square. So, this is not very difficult. So, v star x1 x2 is nothing but d by dt of v of xt. So, if you look at this is not what this is what Vx1, that is x1 and x1 dash. So, x1 dash, let me write it here, plus Vx2 means double V by double x2, that is x2 here, and x2 dash, that is x2 dash. Now, x1 dash is already given as minus x2 plus x1 r square minus x1 square minus x2 square plus x2, and here it is x1 plus x2 r square minus x1 square minus x2 square, and if you simplify, you will get this V star x1 x2 as minus of x1 square plus x2 square, x1 square plus x2 square minus r square. So, you look at this minus is because that we are simplifying this, as we are writing this as x1 square plus x2 square minus r square. Okay, so V star x1 x2 we have already obtained here. Now, we know that if V is our positive definite, because it is taking the value 0 at only at the origin, and in all other point it is taking only positive value, and V star x1 x2 is negative definite if this r is 0 or r is less than x1 square plus x2 square here. So, if x1 square plus x2 square minus r square is positive, then V star is negative definite, and we can simply say that in particular case r equal to 0, the 0 solution of the given system is asymptotically stable, because it is negative definite, is it okay? And on the other hand, when r is not equal to 0, V star is positive definite in the region when x1 square plus x2 square is less than square. So, when x1 square plus x2 square is less than r square, then this is negative, at V star x1 x2 is V star x1 x2 is positive definite. So, V star x1 x2 is positive definite, and there exists a point in the neighborhood of origin where it is taking the value positive. In fact, if you look at here Vx1 x2, so Vx1 x2 is already positive definite, and if V star x is also positive definite, then by the previous theorem here we simply say that your 0 solution of 1 is unstable. So, in case when r is not equal to 0, since r is fixed quantity and x1 x2 can be made smaller and smaller, then we can say that if r is non-zero, we can take small enough x1 x2 such that this quantity is negative here. So, negative, negative, positive, and V star can be made positive, and hence we can say that 0 solution of the given system is unstable when r is not equal to 0 here. So, here we have obtained that the 0 solution is stable, unstable only analyzing your function V of x1 x2. So, here without finding the say a solution of this dynamical system, we are predicting, we are telling that the 0 solution is stable in this region and unstable in this region. So, here we say that if an r equal to 0, we simply say that your 0 solution is asymptotically stable, and if you look at the region x1 square plus x2 square is less than r square, then we simply say that 0 solution is unstable. So, here we are providing the reason also in which your 0 solution is unstable. So, this is not possible when we use the say linear approximation of a given weakly nonlinear system here. So, this is very important say benefit of constructing the Lyapunov function. Now, consider the 2-dimensional system x1 dash equal to minus 6 x2 minus 1 by 4 x1 x2 square, x2 dash equal to 4 x1 minus 1 by 6 x2, and again here we try to predict, try to find out the stability and instability of 0 solution. So, here choose the positive definite function 2x1 square plus 3x2 square. Now, this 2 and 3 will depend on the say coefficient available in x1 dash and x2 dash. You can start with ax1 square and bx2 square. So, let us find out V star here. So, first of all you just look at here that V is a positive definite scalar function. Now, look at the V star is basically 4x1 x1 dash plus 6x2 x2 dash here. So, it is x2 here. So, it is 4x1 x1 dash is basically what, minus 6 x2 minus 1 by 4 x1 x2 square plus 6 x2, it is 4 x1 minus 1 by 6 x2 here. So, if you simplify, this is minus 24 x1 x2 minus x1 is square, x2 is square plus 24 x2 x1 minus x2 is square. So, if you look at here, this will be cancelled out and we will get what, minus x2 is square. If you take it out, then it is what, 1 plus x1 is square. So, if you look at V is positive definite, and V, if you look at V star, then it is taking all the time non-negative value. It can be 0 when x2 is equal to 0 here. So, it means that when x2 is equal to 0, x1 may be anything, but still V star is 0. So, it means that here V star is negative semi definite and V is a positive definite. So, it means that 0 solution is a stable solution here. So, without finding the solution here, we simply say that 0 solution is stable solution here. Okay. So, here we have shown some example by constructing some suitable Lyapunov functions. We have predicted that 0 solution is stable, unstable or asymptotically stable solution. But the important part or the difficult part, most difficult part is how to construct Lyapunov function, because construction of Lyapunov function is nowhere, by no means it is so easy. So, here the important part is how to construct Lyapunov function. So, here we are just considering some cases where we can construct Lyapunov function, and there is some technique by which we can construct the Lyapunov function. So, first method is given as, say, autonomous system, say x dash equal to f of x, and here we will show how to construct the Lyapunov function, and we will try to show that under what condition this autonomous system is having 0 solution, asymptotically solution, stable solution or stable solution or unstable solution. So, consider the autonomous system x dash equal to f of x, where f is function from Rn to Rn, f of 0 equal to 0 and f of x is non-zero when x is non-zero in some neighborhood of the origin. So, it means that here we have assumed that 0 is a isolated critical point. So, because f of x is non-zero in a small neighborhood around the origin. So, 0 is a isolated critical point, and we assume that f of x is differentiable with respect to xi, so that existence and uniqueness may be given. So, only thing we have to check is the stability of 0 solution. So, we already know that the Jacobian function Jacobian matrix J of x is given by dev f by dev x, and it is defined like this. Okay. So, now with the help of Jacobian of f with respect to x, we can construct the Lyapunov function, and the Lyapunov function is given as v of x equal to f transpose x f of x, where f is given as this. So, now how to check that it is the suitable Lyapunov function? For that, we define a matrix M of x, which is given as J transpose x plus J of x, where J transpose is the transpose of J and J is the Jacobian of f with respect to x. And we claim that the suitable Lyapunov function for the system 6 is v of x equal to f transpose x f of x. So, first thing we need to observe that it is a positive definite. In fact, positive definite means it is taking value positive for non 0 x here, and for 0 it is when x equal to 0. So, there is another alternative definition for positive definite, that Vx is positive definite if x transpose Vx x is greater than 0 for all x non-zero, and it is taking the value 0 when x equal to 0. So, if you check look at here, the x transpose V of x is basically f transpose f of x is greater than 0. So, if we can simplify, this is nothing but norm of x f of x is this is basically this quantity is nothing but norm of x f of x whole square, and this is all the time non-negative, and we can say that this is 0 when x f of x equal to 0. So, it means that either f of x equal to 0 or x equal to 0. When f of x equal to 0, we already seen that f of x cannot be 0 other than 0 origin. So, it means that this implies that your x has to be 0 here, right. So, so it means that this x this v of x, which is given as f transpose x f of x, is a positive definite function in a neighborhood of the origin. Now, if the matrix M of x is negative definite in some neighborhood of the origin, then the 0 solution is asymptotically stable here. So, here we talk about the negative definite of a matrix M. So, here also we will discuss a little bit that how given a matrix M of x, how we say that matrix is negative definite, positive definite and negative semi definite. So, here we simply say that M of x, if we look at your Bij, so we simply say that this matrix is positive definite. First let us define positive definite, and negative definite is nothing but minus of M is positive definite. So, M of x is PD positive definite provided that the principal minor is all positive. So, what are principal minor? So, if we look at B11, B12 up to B1n, B21, B22, B2n and so on Bn1 to Bnn. So, principal minor means this is positive. So, it means that B11 is positive, and second is this, it means that B11, B12, B21, B22, this determinant is positive and so on. So, all the principal minor, if they are positive, then we say that M of x, the matrix M of x is positive definite, and it is negative definite if minus of M of x is positive definite, then we say that M of x is negative definite, right. So, here this is the positive definiteness and negative definiteness of a matrix. So, we say that if the matrix M of x is the negative definite in some neighborhood of the origin, then the 0 solution of 6 is asymptotically stable. Let us prove this statement here. So, for that we know that df by dt is equal to j of x f of x, because if you look at f is a function of x and x is a function of t. So, if you want to find out the derivative of this, then it is what, d by dt of f of x of t is basically your f dash x means and x dash t. Now, f dash x is nothing but your Jacobian, so it is j of x, your x dash t, x dash is nothing but f of x here. So, df by dt is given as j of x f of x. So, to find out v star x, it is nothing but vx is basically what? It is vx is basically f transpose f here. So, v star basically it is f transpose dash f plus f transpose f dash. Now, f transpose dash is basically f dash, right, f dash j transpose, it is f transpose, and it is already given here f x f transpose and j transpose f here plus f transpose f dash is basically j x f of x, right. So, we can write here f transpose, and within bracket you can write j transpose plus j and f m. So, if you look at this is nothing but m, so it is f transpose m f m. So, v star is nothing but f transpose m of f. So, if m is negative definite, then we can prove that v star is also negative definite, and hence we can say that 0 solution is asymptotically stable solution. How we say that if m is negative definite, then v star is also negative definite? For that we simply look at x v star x here, it is x f transpose m f x here, x transpose. So, this I can write it, if you look at this is this I can write it x f m square here, right. So, if m is negative definite, then this quantity is basically this quantity is basically going to be negative for all x non-zero. So, here we say that if m is negative definite, then x transpose f transpose m f f x, basically here you can take f of x as y, and similarly y transpose will be what? It is x transpose f transpose. So, it is nothing but y transpose m y here, and since m is negative definite, then this quantity is less than 0. So, it means that v star x is negative definite, and hence your v x which we started with this F transpose F here. This we have shown that it is positive definite, and here V star, which is given as F transpose M of F. When M is negative definite, we simply say that V star is negative definite. So, it means that by theorem we simply say that 0 solution is asymptotically stable solution. And let us take one example based on this. So, determine the stability of the 0 solution of x1 dash equal to minus x1 minus x2 minus x1 cube and x2 dash equal to x1 minus x2 minus x2 cube. So, we can find out Jacobian J here, Jacobian it is your F1, it is your F2. So, Jacobian is basically dever F1, dever x1, dever F1, dever x2, dever F2, dever x1, dever F2, dever x2. So, we can find out dever F1 by dever x1 is basically minus 1 minus 3 x1 square, dever F1 dever x2 minus 1, it is minus 1 minus, so it is dever x2 dever x1. So, it is 1 only. So, this is 1 here, that is all, no other thing, and here it is this is minus 1 minus 3 x2 square. So, that is what we have written here. J is minus 1 minus 3 x1 square minus 1 and 1 minus 1 minus 3 x2 square, and we can find out M. M is nothing but J transpose plus J, and it is given as M equal to minus 2 minus 6 x1 square 0 0 minus 2 minus 6 x2 square. If you look at this is a diagonal matrix with the negative entries on the diagonal. So, we can say that the eigenvalues of the matrix M has to be negative, and there is another alternative definition of negative definite here, that if a matrix has only negative say eigenvalues, then it will be a negative definite, and here in this case since it is a diagonal matrix, then the eigenvalues are nothing but the entries given on the diagonals. So, it means that here M is a negative definite matrix, and hence we can say that by the previous discussion we can say that the 0 solution of the given system by Krasovsky method is asymptotically stable here. Please look at here, it is a sufficient result. It simply says that if M is negative definite, then it is asymptotically stable thing. Is it okay? So, okay. So, this gave a example based on the method discussed before. Now, let us consider one more way. We define construction of a Lyapunov function for linear system with constant coefficient. Now, consider the so earlier one is a nonlinear autonomous system, and this one is a particular case of previous construction. So, we simply say x dash equal to A of x, where A is a n cross n matrix over R whose entries are R. So, let lambda 1 to lambda r be positive, be the distinct real eigenvalues, and u1 to um be the distinct complex eigenvalues of A, such that r plus m is equal to m. So, here we can, since this is all complex eigenvalues, so here we define uk minus 1 as A plus ib and uk as A minus ib. So, it means that lambda 1 to lambda are real eigenvalues and u1 to ums are complex eigenvalues and coming in pairs. So, we define uk minus 1 as A plus ib and uk as A minus ib for k between 2, 4, 6 and so on. So, here A has eigenvalues, this we have obtained here. Now, here we consider the transformation x equal to ty here. So, we can reduce x equal to ty means you can say that x dash equal to Ax is now reduced as y dash into dy. Here we can simply say that x dash equal to here it is t y dash here. So, we can write y dash as t inverse. So, y dash equal to x dash. So, t inverse x dash. Now, x dash is basically what? T inverse x dash is nothing but A of t of y here. So, I can write T inverse At as d here, and we can write this as y dash equal to d of y. The idea is that if we choose the matrix T in a way such that this D represent a triangular system or diagonal system depending on the matrix A, right. So, here we can say that where D is T inverse At, and for system A to be asymptotically stable we require all the diagonal element of D to be negative. So, if we assume this y dash equal to dy, and if we take that all the diagonal element of d to be negative, then we simply say that the 0 solution is asymptotically stable solution. So, that we already know, right. So, what we do not know is that how to construct the Lyapunov function in this case. So, here the Lyapunov function we are defining as v of y as y comma b inner product of y and by, where this b is still unknown, and we simply say the only condition on b we are putting as that it is a n squared symmetric matrix. So, it is a first of all, if it is a symmetric matrix, then we can simply say that v of y is a symmetric v of y is basically a positive definite function. Basically, it is nothing but by transpose y here. So, it is y transpose b transpose y here, and it is nothing but y transpose b of y here. So, v of y is nothing but y transpose b of y is given here, where b is a symmetric matrix. So, vy is given as y transpose b of y here. So, we can say that vy is this. Now, look at the v star y. So, v star y is inner product of y dash by plus inner product of y of by dash. So, we can write this as y d transpose b plus b d y here, because we are just assuming y dash equal to. So, this is what? This is dy by plus y b dy here. So, this I can write it here, and this I can look at here. So, it is y and d transpose b y plus y b d y. So, if you use the inner product properties, then it is nothing but this. If you do not want to use inner product, you can simply use this, and we can still find out this is nothing but the condition here which is obtained here. Okay, so, v star y is given by this. Now, we want to find out whether it is asymptotically stable. So, for that we need to ensure that v star is negative definite, and for that we require that v star y is something like inner product of y. It is written as minus j equal to 1 to n v y j square here. So, this can be achieved if we assume that d transpose b plus b d is equal to minus I. If you look at here, if this is minus I, then this is nothing but y inner product with minus of y, and hence we can say that it is minus I minus summation j equal to 1 to n y j square, and hence it is a negative definite. So, v by definition is positive definite and v star is negative definite, and it means that the 0 solution is going to be asymptotically stable solution. And so, we assume that B is a symmetric matrix of size n such that D transpose B plus BD is equal to minus I here. Now, D is already given to you. D is nothing but T inverse AT, where T is some transformation which we choose in a way says, and then we can solve this and we can get our B here. Now, once your B is given, we can find out the Lyapunov function like this, and we say that if you solve this, then we can say that equation 12 after simplification leads us that B should be, it is minus 1 upon 2 lambda 1, only look at the diagonal terms, minus 1 upon 2 lambda 1, minus 1 upon 2 lambda 2, and up to minus 1 upon 2 lambda r, and then we have it is already given here, and then we have the say diagonal entries corresponding to complex terms. So, it is minus 1 upon 2 a1 and again minus 1 upon 2 a1 and then minus 1 upon 2 a2 and again minus 1 upon 2 a2. So, here all are distinct. Here since they are coming in a pair, so we are writing twice times 2 times minus 1 upon 2 ai's. Okay. So, here your B is coming out to be this. So, once we have B, then we can define V y as y transpose B y and if we use the expression y equal to so x equal to T y, if we use this where T is invertible matrix, then T inverse x, then we can find out the Lyapunov function for the original system x dash equal to A of x here. Okay. So, let us have one example based on this. So, consider a Lyapunov function for 3-dimensional system x dash equal to a of x, where A is given as this matrix 0 1 0 0 0 1 minus 12 minus 20 minus 9. So, eigenvalues you can find out minus 1 minus 2 minus 6. So, we simply say that here 0 solution is asymptotically stable solution. Let us try to prove that we have done, we can conclude with the help of theory which we have discussed earlier. Now, let us re-verify by constructing the Lyapunov function. So, corresponding eigenvector we can find out, and once your eigenvectors are there, then you can consider your T matrix as the matrix of eigenvectors. So, we write T as 1 minus 1 1, 1 minus 2 4, 1 minus 6 36, and we can write D as T inverse A T, that is the diagonal form corresponding to matrix A. So, T is equal to minus 1 0 0 0 minus 2 0 0 0 minus 6, and we can find out x equal to T y to transfer our system as y dash equal to d y. Now, D is of this form. So, with the help of D we can find out the matrix B, that is I think the solution of B transpose, I think it is given in D transpose B plus B D equal to minus I. So, D is already given, we can simply plug in the value and you can find out the expression for B here. So, once we have this, then we can find out B, and it is given as 1 by 2 0 0 0 1 by 4 0 0 0 1 by 12, and then the Lyapunov function for the system y dash equal to dy is given as inner product of y by or by transpose y, and you can simply say it is nothing but 1 by 2 y1 square plus 1 by 4 y2 square plus 1 upon 12 y3 square, and you can see that these are this Vy is positive definite because it is taking value 0 only on the origin y1 y2 y3. Now, we already have this relation that x equal to Ty. So, here y equal to T inverse x. So, T is invertible. So, we can use this and we can have we can obtain the Lyapunov function for the system x dash equal to Ax by putting x equal to Ty by putting y equal to T inverse x here, and we can get the Lyapunov function for x dash equal to A of x here. Okay. And here by the way we have already obtained B in a way such that V star is negative definite. So, it means that solution is going to be asymptotically stable solution. So, now let us look at one more kind of a method to construct the Lyapunov function, and here we construct the Lyapunov function as total energy function. So, for that let us consider the scalar differential equation u double dash plus g of u equal to 0 here, where g is continuously differentiable function for norm of u is less than k, where some k is some constant which is positive, and u of g of u is positive if u is non-zero. Now, by the continuity g of 0 equal to 0 here, and if we can write down this system 16 as x1 dash equal to x2 and x2 dash equal to minus g of x1. So, we can write down the scalar differential equation as a system like this, and which x1 and x2 equal to 0 is an isolated critical point. And if we consider g of u as a restoring force of a spring or pendulum acting on a particle of unit mass at a displacement a from the equilibrium, and let u dash be the velocity of the particle. Idea is that if gx1 is basically a force which will try to reduce the displacement to the initial place, means it is trying to say make our system in a original position. So, it is a restoring force basically we have, and u dash is the velocity of the particle. Then the total energy we can say that it is what? It is basically 1 by 2 u dash square. Basically it is nothing but the kinetic energy. Kinetic energy is basically what? It is 1 by 2 mass. If we look at m as 1, then it is 1 by 2 of b square. So, half m b square. So, it is a total energy kinetic energy of the system here. And if you look at the second part is basically that g of sigma is basically the restoring force, and if we calculate the restoring force between 0 to u, we can say that it is nothing but potential energy. So, we can say that 0 to u g of sigma d sigma, it is a potential energy, and the first one is the kinetic energy. So, it is a kinetic energy due to velocity. So, it means that the total energy is given as 1 by 2 u dash square plus 0 to u g sigma d sigma. And for the origin to be asymptotically stable, this total energy would have to decrease at least to 0 as a function of time as t tending to infinity. Idea is to that your system is going to a stable solution, going to be a stable position if the total energy is reducing, and it will be it will remain in a stable position if the total energy is not increasing. If it will remain means in a minimum value, then it will not change its stability behavior. So, idea is that if origin is asymptotically stable solution, then this total energy is tending towards 0 here. So, this suggests that to check the stability of 17, we will select this total energy as a Lyapunov function, and we write Lyapunov function as v of x1 x2 is equal to 1 by 2 x2 square plus 0 to x1 g of sigma d sigma. And this function is defined between this omega is all those x1 x2 says the norm of x1 is less than k and norm of x2 is less than infinity, and we can easily check that v of 0 comma 0 is equal to 0 here. And here we can easily check that v x1 x2 is a non-negative. In fact, it is taking v x1 x2 is a positive definite function. Here we are putting the condition that u gu is greater than 0 here. So, if you put u gu is a positive, so it is your behavior of gu is like this. So, it is your u and it is of g of u. So, it means that if u we take between here to here between 0 to x1, then it will take only the positive value. So, this integral is taking only the positive value. So, if it is positive, it is positive, then we say that v x1 x2 is all the time positive, because negative it is vanishing only on the point when x1 is equal to 0 and x2 is equal to 0. So, it is vanishing only only on the origin, and in all other point it is taking only the positive value. So, here we simply say that v x1 x2 is given as this, which is considered to be as total energy function here. Now, this also suggests that in general we take Lyapunov function as the sum of the squares or say quadratic functions here. Anyway, now let us take one example based on this. So, consider a 2-dimensional system x1 dash equal to minus x1 minus x2, x2 dash equal to x1 minus x2 cube, and investigate the stability of its equilibrium solution 0 solution. Now, let us select a scalar function x1 square plus x2 square. In fact, most of the time we consider x1 x2 as some a x1 square plus b x2 square, and then we fix the value a and b depending on the say requirement. So, which is first of all this is a positive definite, and if you look at the derivative of v along the system 18, then it is what 2 x1 x1 dash plus 2 x2 x2 dash, and put the value of x1 dash and x2 dash, and you can say that v star x1 x2 is given as minus 2 x1 square minus 2 x2 power 4, and if you look at this is nothing but negative definite here. This will be 0 only when x1 and x2 both are 0, and hence we can say that we have a Lyapunov function which is positive definite and whose derivative is negative definite, and hence the 0 solution is asymptotically stable solution here. So, with this we end our discussion, and we say that Lyapunov direct method of finding the analysis based on the Lyapunov function. So, the main difficulty part is to construct the Lyapunov function, but once we have the Lyapunov function, suitable Lyapunov function, then we can directly say the stability, instability and asymptotically stability of 0 solution of a given system without finding the other solution of the dynamical system. And this is equally valid by saying that we can check stability of any equilibrium solution of dynamical system, because we can always translate our dynamical system so that your equilibrium solution is act as a 0 solution. This we have already discussed, how we say change, how we shift our origin so that a non-zero critical point will take a 0 critical point of a given nonlinear system here. So, here this Lyapunov stability we have discussed that if we have suitable Lyapunov function, then the 0 solution of given dynamical system is stable, asymptotically stable or unstable under certain condition. So, with this we stop, and that is all for this class here. So, thank you very much for listening us. Thank you.